Hi. In our last class, we talked about simple regression model. We said that how does the OLS is able to does the job and find the coefficients of beta hat 0 and beta hat 1 by using a data from a sample. In this class, we're going to talk about the properties of those beta hat 0s and beta hat 1s. For instance, what is the expected value of the beta hat 1? What is the variance of beta hat 1? How does the distribution of beta hat 1 look like? In order to answer questions like this, we should make some assumptions. Basically, we are going to talk about Gauss Markov assumptions in simple linear regression model. So there are 5 assumptions that we are going to make in this chapter, and without those assumptions, we cannot use OLS. Well, we can, but we should not rely on the answers that we get. So because without those assumptions, our estimates are going to be maybe biased. Without those assumptions, our interpretation is not necessarily causal interpretation. Without those assumptions, maybe our estimates are not even accurate. So we need to make these assumptions and we really rely on them to continue our journey in regression analysis. But before that, let's clear out some of the definitions. All right. So you already know all these definitions, and so let me write down the equation that we used to work with, and then we're going to try to connect these definitions to what we already know. So for example, going back to our main research question, we were interested to see if there's a relationship. Sorry, let me change my pen. We wanted to see if there is a relationship between, let's say, wage and education in the population. So that was the question of interest. We want to see if we change the education in the entire population, what is the impact on the wage, right? So that's what we were interested. But we said that it's not possible because we cannot collect data for the entire population. So we end up working with a sample, right? So we already know what is population. Population is the entire group of subjects that interest us, like individuals, firms, cities, and etc. So in our example here, we're talking about all US citizens that we want to collect information under education and wage. Then what is sample? Sample is part of that population that we actually observe. So we tend to say that the entire population is not observable. And when we say it's not observable, we mean it's not practical to collect information for all the population. However, the sample is going to be observable, right? So for instance, look at the data that we have in Wooldridge textbook. So I can observe the information for a sample of data, for a sample of the population. Then what is parameter and what is estimator and what is estimate? Parameter is a characteristic of the population whose value is unknown but can be estimated. So let me actually write down our regression model. So we say wage is going to be equal to beta 0 plus beta 1, education plus some unobserved factors, right? So this is our this is the model that we're interested to explore for the entire population. So these are going to be called parameters. So beta 0 and beta 1s are our parameters here, right? Parameters. These are some characteristics of the population that, by the way, the value is unknown, and we never get to know what is the exact value of these parameters. However, we need to estimate them, right? So it says that it can be estimated. So in our regression analysis, how do we estimate these parameters? By using OLS. So what is OLS? OLS is our estimator. So the next term is going to be estimator. It's a sample statistic, it's a rule, it's a function, like average, like OLS, right? These are some rules, some functions that will be used to estimate the value of the population parameter. So in our example here, what is population parameter? Beta 0, beta 1. What is the estimator? OLS. What are we estimating? The numerical values for beta 0, we call it beta hat 0, and beta 1, we call it beta hat 1, right? So that's things that we're estimating, we call them estimate. So estimate is the specific value of the estimator that is obtained in one particular sample. So in our example, we are talking about beta hat 0 and beta hat 1. So estimator is going to be OLS, and parameter is going to be beta 0 and beta 1 in the simple example that we're exploring. And then finally, statistical inference. The statistical inference involves using the sample to draw a conclusion about the characteristic of the population. So we use sample to draw inferences about the population because it is often practical to scrutinize, impractical to to consider the entire population, right? This is nothing new. We already know that it's impractical, it's impossible for us to work with the entire population. So whenever you want to say something about the population, you have to look at the sample and then try to infer things from sample to population. So this is called the statistical inference. All right. Now let's look at another term, which is biased. So what is bias? What is biased sample? And what kind of biases we have? So in general, any sample that differs systematically from the population. Remember, I have an entire population. Let's say this is the entire US population. I'm collecting information under education and wage and etc. And a good sample is that if I do it randomly, so I go through the entire US population, go over all the 50 states, and then collect information from all the entire population randomly in the US. So this is called a good sample, right? But if I don't do that, if the sample, so if my samples differ systematically from population, so for instance, if I only collect information from here, from this state, or from here, from East Coast, West Coast, whatever, if I'm collecting information like that, then my sample is going to be biased. So we call it's a biased sample, right? Now let's see what types of biases we have. So the first one is called selection bias. Selection bias happens when the selection of the sample systematically, so this is key, it systematically excludes or underrepresents certain groups. So imagine, I'm interested in coming up with an estimate for the average rainfall in US, in the entire country. So there's nothing wrong with that. So this is the entire population. So again, the statistics that I'm looking for is the average rainfall, right? Now, if I now go ahead and collect information only from the East Coast states in the part of the country, so this is going to be called selection bias. We are systematically excluding or underrepresenting the drier areas, the drier states, the central states, right? So this is called selection bias. Then we have another bias called self-selection bias. Selection bias and self-selection bias sometimes are used interchangeably, and sometimes people get them confused, but it really doesn't matter. As long as there's a selection bias, you can just call it selection bias. But what is self-selection bias? Self-selection bias happens when we examine data for a group of people, for a group of specific people who have chosen to be in that group. So let me give you an example. Imagine I come to business school and go to econ and finance department, and I ask them, do you like econ? So what do you expect to hear? So of course they're gonna like econ. Or I go to mathematics department and then I look at their math grade. So of course this number is going to be biased upward, right? So this is because the sample has a self-selection bias. People chose to be there, right? So we call it self-selection bias. The next type of bias is survivor's bias. So or sometimes we call it survivorship bias. So survivor's bias, it happens when we look only at survivors, right? And this happens a lot in finance literature, especially, if you're looking at, for instance, looking at the returns on mutual funds. And you say, the average return for mutual funds in the past 10 years, let's say it was 20%. So usually people are ignoring that the companies, the funds, the mutual funds that are reporting the return, they are the one who survived. So the one that gone out of business, they're not there to report anything, right? So the number that you're seeing at the end of the day may be biased. So you have to make sure you control for these biases. And then finally, we have non-response bias. So this is also very common and usual when we are dealing with survey data. So this is a systematic refusal of some groups to participate in an experiment or to respond to a poll, right? So for instance, if you're collecting survey on people and ask them, are you an alcohol abuser? And when you say abuser, then they want to say that, okay, I'm not going to answer this question. Or if you are collecting even the census data, when people send you you receive some forms from census in your mail and it's asking for your income. There's a good chance that many people are not going to respond that question, right? So if your sample is suffering from those kind of biases, we call it non-response bias. Okay, and then finally, how do we deal with these biases? The best way to solve the problem with these biases is to do a random selection. If you make sure that your sample is a very, very randomly sampled from the entire population, then there's a good chance that you're not going to deal with any of these kind of biases. So the answer is going to be random selection. Okay, so random selection can address these biases. However, be careful. If your sample size is small, you cannot do anything with that. So if my sample size is only 10 and I have 50 states, there's no way I can collect one observation from each state. So this sample is going to be biased anyways, and it has a small sample bias. So you cannot deal with small sample bias even if you're doing your sampling process completely at random. So be careful. Usually we need sample sizes large enough, and this large enough is very subjective. Depending on the field, enough has different interpretation. So for instance, again, it depends on what field you're working on. But in the textbook, sometimes it says that sample size greater than 30 or 50 is large enough. But I don't want you to get obsessed with that number. There's no rule of thumb. It all depends on the context. For instance, in financial time series, 30 is nothing. It's nothing. So you need hundreds of observations. But maybe in some other cross-sectional data, in an experimental lab, which is done in an experimental lab, maybe 30 is good enough, right? All right. Now let's talk about sampling distribution. So in housing, you may have heard, in real estate, what matters is location, location, location. So the three most important concepts in statistics are sampling distribution, sampling distribution, sampling distribution. So what is sampling distribution? What is it trying to tell us? Okay, let me give you an example of what I mean by sampling distribution. From our previous lecture, do you remember that we say, okay, there is some imagine the green dots are the population, they are the entire population. And we have this imaginary population regression function that we said, in real life, in real world, it's not observable, but it is unique. And then we went ahead and worked with a sample of this green dot. So let's say we work with this sample, something like that. And we said, okay, OLS is going to use this sample and come up with a sample regression function. Let's call it sample regression function because if I work with another sample, if I work with a blue sample, I get another line. If I work with a black sample, and when I say blue-black, I'm talking about different observations from the population, right? Different samples from the population. So this simple regression function, we talked about it, it's not unique. So if I work with another sample from the population, let's use blue color. Imagine, let's say we get this one. So I call it sample regression function number 2. Again, if I work with blue dots, I get SRF2. If I work with red dots, I get SRF1. But remember, each of these things come with an estimate for beta hat 0 and a slope, beta hat 1, right? So again, here for the red one, I have beta hat 0, slope, intercept, and slope, beta hat 1. Now let's focus on one of them for simplicity. But you can imagine, all the beta hats are going to have their own distribution. But let's say I do this sampling, I use these different colors thousands of times, right? So for my SRF1, I have, let's only focus on beta hat 1. I have one beta hat 1, right? For SRF number 2, I have another beta hat 1, right? So let me use a superscript to make distinguish between 1 and 2. So this is beta hat 1, beta hat 1, 2. If I work with another sample, let's say sample number 10, then I have another beta hat 1. Let's call it 10, right? So at the end of the day, depending on how many samples that I'm drawing from the population. So remember, I have the entire US population in the example of wage versus education. I can go ahead and collect samples thousands of times. Thousands of times I can collect information on, let's say, 100 people in the entire country, right? So if I repeat that, I will get, and I use OLS to estimate beta hat 0, beta hat 1. At the end of the day, I will get thousands of these numbers. Again, this is the number of these beta hats is going to be equal to the number of sampling that we're doing from the population, right? Let's say I have thousands of these beta hats. If I have thousands of these beta hats, and specifically here beta hat 1s, so I can plot the distribution. I can plot the PDF, right? So basically I can, tabularize the frequency, come up with the density function, and literally I can plot it. So maybe at the end of the day, the distribution for our beta hats is something like normal. And actually we're going to make some assumptions. Based on those assumptions, we're going to say that, you know what, the distribution is normal. Again, this is a topic for our future classes. But for now, let's assume that at the end of the day, if you do these repeated sampling thousands of times, you will get a distribution for your beta hat, and the distribution is going to be normal, right? Normal distribution. Now, when I have the distribution, so I can actually tell a lot more about my regression coefficients now. For instance, I can say what is the expected value. What is the expected value of beta hat 1? I can say what is the variance of beta hat 1. And these are very important properties, right? Because at the end of the day, remember guys, we cannot observe what is beta 0 and beta 1. And when I give you one data set, so this is a very subtle point. I want you to, just listen to this part maybe many times until you feel that you get it. So again, beta 0, beta 1s are not observable. At the end of the day, you are going to work with one sample. Look at the Wooldridge data set. The data set wage is one sample from the entire population. So maybe that one sample is red dots. Maybe that one sample are blue dots, right? We never know. But whatever it is, at the end of the day, when you use OLS, you get one beta hat 0, one beta hat 1, right? So let's go to the second bullet point. So this means that you cannot say whether a particular sample, the sample that, for instance, you're using the in the Wooldridge textbook, you cannot say that if a particular sample estimate is above or below the population parameter, because we don't know the value of the population parameter, right? So at the end of the day, I get a number for beta hat 0, beta hat 1, but I never know how close or far are these numbers from beta 0 and beta 1, which are the population parameters. Right? This sounds a little abstract, but I hope that you realize what we're trying to do. We're trying to come up with these numbers, and we hope that these numbers are as close as possible to something which is unobservable. So I have one sample, and with one sample, this is given, beta hat 0, beta hat 1. But if I make some assumptions, so these are the Gauss Markov assumptions that we need down the road. If I make some assumptions about the unobserved factors specifically and things like that, I can say something about the expected value of these beta hats and the variance of these beta hats, and more importantly, the distribution of these beta hats. Why does it matter? Because I can tell at least if on average these beta hats on average are close enough to the population parameter like betas. So this is, again, if it is on average close, we give it a name. We say it's unbiased. That's the definition of unbiasedness. I'm going to officially present it in the next video, but that's literally the definition of unbiasedness. If on average these beta hats are close to the unobserved beta, right? It's a good news. We call that our estimate is going to be unbiased. So that's something. So I do care about the expected value. Why do I care about the variance? Because if the variance of these beta hats are smaller, it's a better news, right? So for instance, if I have SRF3, SRF4, it's bad news because the variance of the slope is high, and I can never know, at the end of the day, you're going to say that, okay, what's the relationship between education and wage? In each sample, the numbers are way different. So I don't like this high variance. So we don't like high variance. So if the variance is small, it's good news. We're going to explore all these things down the road, but this is basically a big picture, a preview why we need to make those assumptions. Because without those assumptions, without Gauss Markov assumptions that we're going to make down the road, we cannot say anything about the expected value of beta hat, the variance of beta hat, and then the distribution of beta hat. Why do I care about the distribution of beta hat? Because if I have a distribution of some random variable, then I can make confidence intervals. I can say, let's say with 95% probability, this interval is going to contain your beta hat 1 or beta hat 0. So this is important. For hypothesis analysis, we do need to rely on the distribution for our parameter, for our estimator, right? So the sampling distribution, I'm on the third bullet point. The sampling distribution of a statistic is the probability distribution or density curve that describes the all possible value of an estimator. So this is basically what we said. These are all possible values of your beta hat 1 or beta hat 0. We can sort them and plot them here. And this is the PDF for beta hat 1. I can plot the PDF for beta hat 0 as well. All right. So this is very important. And now in the next set of slides, we're going to talk about those assumptions, which we call it Gauss Markov assumptions in linear regression model. All right, so let's stop this one and see you in the next one.